When dealing with limits of trigonometric functions, there are three things that we must know. The limit of sine theta over theta as theta approaches 0 is 1. That's the first thing we must know. The second thing, which I will do in red, the limit of cos theta as theta approaches 0 is equal to 1. The third thing that I will be doing in green, the limit of cosine theta minus 1 over theta as theta approaches 0 is equal to 0. And these are the three things that we will use for basic trigonometric function when we are finding the limits for such functions. If we are to plug in the values as normal, where we have the limit as theta approaches 0, if we are to plug in the 0 as normal, where we substitute this value here for theta in the function, we will end up with this, which would be indeterminate. But in actuality, it is 1. I will prove that soon, but let's look at the other one. Cos theta. The limit of cos theta as theta approaches 0, if we are to plug in the 0, cos 0, we would get 1. So this one, we can do a direct substitution and we get 1. Cos theta minus 1 over 0. And of course, you're finding the limit of this function as theta approaches 0. If we do a direct substitution, we would have 1 minus 1 over 0. And that is because cos 0 would be 1. So that's the reason for the 1 there. So this would be indeterminate because this would lead to 0 over 0, which is indeterminate. So I will prove to you how this function is equal to 0, and how the limit of this function is equal to 1. To understand this, we must first understand a few things. Things that we probably already know, like the squeeze theorem, and understanding a little about the unit circle, as well as find the area of a triangle, area of a sector, and the area of an arc. So let's get into that, starting off with squeeze theorem. So squeeze theorem is this important theory in mathematics that says if there is 3 persons in a race, person 1, that's in that orangish yellowish color, and person 2, person 3. If the yellow person always comes first in the race, and this person always comes second, this person always comes third, for any occurrence that these two are the same, then this middle one will be the same as well. So you have 3 different balls of 3 different weight. Ball 1, ball 2, and ball 3. If you roll those balls down a hill, and if in every instance, these balls has different mass. For every instance, this always reach here first, this comes second, and then this would always fall in the third position. For any occurrence that these two, this and this, reaches the finish line at the same time, then based on squeeze theorem, this center one would also reach at the same time. So basically what the squeeze theorem say, this here is always between this. A squeeze theorem is also known as sandwich theorem for those who don't know. So they are the same thing. You can do your research on it if you want further clarification. So this is basically what squeeze theorem say. So if I have a function f of x and it's squeezed between two functions g of h, or let me say x, g of x and h of x, then whenever h of x is equal to g of x, based on squeeze theorem, f of x would also equal to these two functions. And that's basically what squeeze theorem says. So let's take a look on what all of this means when we go back to the function, this function. Let me show you here, this function. Remember, we're trying to prove that this function is 1 using squeeze theorem. The limit of this function as theta approaches 0 equal 1, and we're using squeeze theorem to prove that. Now, the unit circle is a circle with a radius of 1. So let me draw, and then we are going to make a triangle within this quadrant here. So let's make our triangle. If I draw a line from here that touches there, then as long as it is from the center to the circumference, then the length of that line is the length of the radius, which is 1 in this case. That's our straight line. Now if I draw a line parallel to this line, starting from this point, and cutting through this line here, I would make a right angle triangle. And then from there, we're going to make a line tangential to the circle itself that cuts through this line, making a bigger right angle triangle. That's our tangential line. This point is O, which is the origin. This point is D. This point is A. This point is B. And this point is C. And we know that from here to here is the radius, which is 1, but we're going to write r. So doing this, we see two triangles, a small one and a big one, one inside one. So triangle AOD is inside triangle BOC. The functions that will be used in the squeeze theorem are the three shaded regions shown here. As we can see here, the function that would be sandwiched between the two other functions would be the sector. The sector would be sandwiched between the smaller right angle triangle and the bigger right angle triangle. So now we are going to use trig ratios. You may have seen this in school. So, toa. This is what we're going to use to define our lines. So for the line here, let me highlight that line there. If we want to find that line, given that we already know r, which is our hypotenuse, so remember that the hypotenuse is r. So to find the magnitude of this line using trig ratios, this is how we do that. Let me label each side so we can see which side is the opposite, which side is the hypotenuse, and which side is adjacent. So with that being shown there, we can see a little clearer what we're getting to. And I hope that you are understanding what I'm getting at, or else I will have to make a next video. We see that the hypotenuse side is r, so let's find the two unknowns, which are the adjacent and the opposite side. So firstly, the adjacent side. If we want to find the adjacent side, we need to use a trig ratio that includes the adjacent side and the already known hypotenuse side. So we're going to use the cos trig ratio. So the line OA would be equal to, we know that the hypotenuse side is r, so this would be equal to cos theta equal a over r. And if we transpose for a, which is the unknown side, we would have, and now we have this side. Moving to the opposite side, which is dA, let's write that in the next column. So dA, which is the opposite side, if we look back on our trig ratio, or not the trig ratio, but what we use to memorize, we see that we have the opposite side here, which is our unknown, and we are given r for the hypotenuse. So let's use the sine trig ratio to find the side, this side. So dA would be equal to sine theta equal the opposite side over the adjacent side. And as we see above there, that the hypotenuse is r. So sine theta would be equal to the opposite side over r. And if we solve for the opposite side, we'd have r sine theta equal the opposite side. So now we have here. Now, how the squeeze theorem work, we see that we have three shaded section here. The green shaded section, and the red, and the yellow. So the green shaded section is our first function, and we are going to find the area of that triangle. So we know that the area of a right angle triangle is half base times height. In this case, the base is the adjacent side. So half base, which is r cos theta, so half of r cos theta times the height, which is r sine theta, which is the opposite side, and that would be our first function. Let's write that. So half base times height, our base is r cos theta, our height is r sine theta. That's our first function. The next section, which is the sector, which includes that triangle along with the red section. In order to find the area of a sector, we have half r squared, which is the radius, half the radius squared times the angle. Let me put that as our middle function. And then the bigger triangle, which again is half base times height. This time, the height is tangential to the circle. So instead of using sine for the height, we will have tan theta. This line, because it is from the center and it touches the circumference of the circle, then that would be the radius. So from ear to ear, let me do that in blue, from ear to ear would be the radius. So the base of this bigger triangle is the radius of the circle, and the height of that triangle is tan theta. So we're going to do half base times height again. If we pay close attention, we see that there are two r in this function. There's a r squared here, and these are multiplying each other, so it will be r squared as well as these r. And next common thing we can see is there's a half in all these. So we can drop the common and work with what's not common. So let's do that. We can rewrite tan theta as sine over cos. Now if we divide through by sine theta, this is what we'll be left with. Next, we flip these. So we will carry this on this side, carry this on this side, and flip this. So let's do that. For these two outer functions, we already know the limits. We know that the limit for 1 over cos theta as theta approaches 0 is equal to 1 over 1. We also know that the limit of this function as theta approaches 0 would be 1. And if you recall what squeeze theorem says, if I have this where there's a 1 on this side and there's sine theta over theta in the middle, and on this side as well, wait a minute, this sign should be greater than, so greater than here as well, sorry about that, and here this is 1. That simply leads to say that the limit of sine theta, let me write that, the limit of sine theta over theta equals 1, and this is based on squeeze theorem. The next thing that I want to prove is cos theta minus 1 over theta. We checked this already and we know if we plug in 0, we will end up with 0 over 0, which is indeterminate. So we know straight off the bat that we can't do this. If you recall earlier, we did some rationalizing in this playlist. So we're going to rationalize the numerator. So let's do that. So if we rationalize the numerator, we'll have cos theta minus 1 over theta. And we know to rationalize, we multiply by the conjugate of the numerator. So multiply by cos theta plus 1 over cos theta plus 1. From this we will result in cos squared theta minus 1. In the denominator, theta times cos theta plus 1. Put this in a bracket. Now from the unit identity, that is what I call it, the unit identity, let me write it right here. Cos squared x, in this case theta, let me use theta for consistency. Cos squared theta plus sine squared theta equal 1. So if I rewrite this and equate it to sine or negative sine, it will be equal to what's in the numerator. So let's transpose for this. This the subject of the formula, if we must. So you would have cosine squared theta, because it's a positive 1 on this side, you'd have minus 1 equal sine, well, a negative sign since there's a plus, sine squared theta. So this is what is on the numerator. So we can replace it with negative sine squared theta. So what we do is this. Negative sine squared theta over, let's look what was in the denominator, theta cos theta plus 1. Theta, the cos theta plus 1. That's inside the bracket. I can now rewrite this as negative sine theta over theta times sine theta times 1 over cos theta plus 1. This is the same thing as this fraction here. So don't be confused. From limits theorem, we know that if we're finding the limit of a function a times function b times function c, we can find the individual limits and multiply them. So this can be the same as the limit of a times the limit of b times the limit of c. So we're going to find the limit of this, this, and this. From before, we already know the limit of that. So that would be a -1, right? So let's put that down first in blue. So -1, the limit of sine theta as theta approaches 0 is 0, as we already know. So let's put that 0 here. And for the final function, for this function, the limit of that function would be 1 over 1 plus 1, which is equal to 1. But since 0 is in the multiplication, it automatically equals to 0. So all of that proves that this function here, let me go back up. This function in red is not indeed indeterminate, but is equal to 0 as theta approaches 0. One more thing that we must note is that as sine theta over theta equals 1, and remember this is the limit of sine theta as theta approaches 0. This is important. It must be approaching 0 for this to be true. So the limit as theta approaches 0 of sine theta over theta is equal to 1. By that same principle, theta over sine theta equals 1. And that's it for this video because it's too long to do any examples. In the next video, I will do some examples. So thank you for watching.